So in this video, I'm gonna be talking about few-shot learning, but we are using these pre-trained language models. And the task that we want to solve is intent detection. And it is in the framework of supervised, so it's a supervised setting. And we are talking about isotropization because these pre-trained models have the problem they are anisotropic, so we want to make them isotropic. So I'm gonna be focusing on this important paper in 2022. It is challenging to train a good intent classifier for a task-oriented dialogue system with only few annotations. Recent studies have shown that fine-tuning pre-trained language models with a small amount of labeled utterances from public benchmarks in a supervised manner is extremely helpful. However, we find that supervised pre-trained yields an anisotropic feature space. For example, the features are just in a small cone, so you miss the rest of state space, which is quite large. Inspired by recent research in isotropization, we've proposed to improve supervised pre-training by regularizing the feature space towards isotropy. So we propose two regularizers based on contrastive learning and correlation matrix respectively, and demonstrate their effectiveness through extensive experiments. Our main finding is that it is promising to regularize supervised pre-training with isotropization to further improve the performance of few-shot intent detection. So this is an illustration of our proposed regularized supervised pre-train. It denotes supervised pre-training, which makes the feature space more anisotropic, which leads to better performance and few-shot intent detection. Here we have our supervised loss, but these are isotropic regularizers. And of course, this is a perfect isotropy instead of a very narrow cone that features are inside this narrow cone. We have to make it like this perfect isotropy. And some papers use the word whitening. And there is a paper whitening approach to this. There are many papers about this idea, and it's very important. Unfortunately, many people talk about it, especially in the framework of ChatGPT and those things. They never talk about these real problems. So can we improve supervised pre-training via isotropization for few-shot intent detection? Anisotropy is a geometric property that semantic vectors fall into a narrow cone. This narrow cone. It has been identified as a crucial factor for the suboptimal performance of pre-trained language model. Fortunately, isotropization techniques can be applied to adjust the embedding space and yield significant performance improving in many tasks. Isotropy, a key geometric property of semantic space of pre-trained language models, and recent studies identify the anisotropy of pre-trained language models, which is also known as the representation degeneration problem. Gao used to say it is representation degeneration. It means that it is a degenerate case, and word embeddings occupy a narrow cone in his article, which suppresses expressiveness of pre-trained language models. And to resolve these problems, various Methods have been proposed, including spectrum control, flow-based mapping, whitening. This word whitening, recently people use this word instead of saying all of these things about anisotropy. So we just need a whitening transformation. Of course, some people use clustering methods, like in 2021. Despite their effectiveness, these methods are designed for off-the-shelf pre-trained language models. The interaction between isotropization and fine-tuning remains underexplored, so it is underexplored. There are 3 contributions. The first study on the isotropy property of pre-trained language model for few-shot intent detection, shedding light on the interaction of supervised pre-training and isotropization. We improve supervised pre-training by devising 2 simple yet effective regularizers to increase the isotropy of the feature space. We conduct a comprehensive evaluation and analysis to validate the effectiveness of the proposed approach. First, they present a pilot experiment to gain some insight into the interaction between isotropization and fine-tuning pre-trained language models. So they adopt the standard measurement isotropy, which is the mean of Z. Z is a partition function. This partition function. And V is just a matrix of stacked embeddings of n utterances. C is just this capital C here is a set of unit eigenvectors. So we are minimizing or maximizing over all possible eigenvectors of V transpose V. To observe the impact of fine-tuning on isotropy, we follow intent BERT. To fine-tune BERT with standard supervised training on small set of an intent detection benchmark. So to examine the effect of isotropization on a fine-tuned model, we apply 2 strong isotropization techniques to intent BERT: dropout-based contrastive learning and whitening transformation. The former, which is dropout-based method, is in a contrastive, it fine-tunes just in a contrastive learning manner. But the latter one, which is the whitening transformation, transforms the semantic feature space into a isotropic space with using a matrix transformation. And these methods are highly effective. So you see the impact of whitening here in this picture. Whitening transformation leads to perfect isotropy, but has inconsistent effects on the performance. So few-shot intent detection targets to train a good intent classifier with only few labeled data. So they propose to learn intent detection skills on a small subset of public intent detection benchmarks by supervised pre-training. So they have a source data for pre-training where number of source is the number of examples that they use for source train, for the source domain. The fine-tuned pre-trained language model can be directly used on the target dataset. It has been shown that this method can work well when the labeled spaces of the source and the target are disjoint. Specifically, the pre-training is conducted by attaching a linear layer on top of the utterance representation generated by pre-trained language model. So this H sub I is the representation of the I's utterance. So we have some parameters, and so we just say theta as the reference to all of these parameters. We just this is a contrastive cross-entropy loss. We want to minimize it with respect to these parameters. After supervised pre-training, the linear layer is removed, and the pre-trained language model can be immediately used as a feature extractor for few-shot intent classification on target date. But to mitigate the anisotropy of the pre-trained language model, we propose a join. We just regularize it. So this term refers to our work for fighting about anisotropy. So this is isotropization work, and lambda is just a hyperparameter. The aim is to learn intent detection skills while maintaining an appropriate degree of isotropy. So we miss by this loss. It may not be perfect. This may not be perfect loss, but because it's a trade-off between how isotropic your data has become. In the representation mode, in the representation space, and how good you are doing your traditional cross-entropy method. So this regularizer that I'm talking can be defined here if you just use a dropout contrastive loss. So our regularization, that's why I always say contrastive learning is very important for isotropization, to fight anisotropy. So we have positive and negative examples. As you know, if you see my playlist for contrastive learning, this playlist is about few-shot learning, but I have a playlist for contrastive learning where I say that there are different methods for contrastive learning. So the above regularizer reinforces isotropization implicitly, but we propose a new regularizer that explicitly forces isotropization. So they are introducing another regularizer. The perfect isotropy is characterized by zero covariance and uniform variance. So a covariance matrix with uniform diagonal elements and zero non-diagonal elements. Isotropization can be achieved by endowing the feature space with such statistical property. So we base the regularizer on this correlation matrix. So it's just a Frobenius norm, and I is the identity matrix, but the Z, you know sigma. This is the correlation matrix, and the entries of that are Pearson correlation for each one. For example, sigma ij is just a Pearson correlation coefficient between the i's dimension and the j's dimension. So we want to push the correlation matrix toward this identity matrix during training, because we want uniform variance and zero covariance. Zero covariance, it means off diagonal we don't want anything, it wants to be zero, but the diagonal we want to be as close as possible to the identity. So the two regularizers can be used together here. So we have cross entropy for source domain as usual, but we have two regularizers. If you're not familiar with Pearson correlation coefficient, you can see that this is just the expectation of xy minus expectation of x times expectation of y, and with this denominator. And you see, we create, because we have positive negative pairs, we can create correlation. We want to be as close as possible to the identity matrix. So the difference is our loss for one of our regularizers, which is explicit. And these are the hyperparameters. We can experiment it with different pre-trained models, such as BERT or Roberta. Or in biomedical domain, we work with BioBERT, which is very nice, or SciBERT or PubMedBERT. There are many pre-trained models that all of them have anisotropy problem, so we try to do isotropization. There are many methods, many data sets, and we expect that for 2-shot, the performance to be lower than 10 shots. As you see, all of them are lower. The same for other data sets, all of them are lower. As you see, all of them are lower. The same for other data sets. And different methods, for example, you can compare Roberta and you can do whitening over that, or you can freeze with Roberta. There are different combinations. This is the comparison between using covariance matrix and using correlation matrix. Because it has slight difference, can either use correlation matrix or covariance matrix. So we have identified and analyzed the anisotropy of the feature space of a pre-trained language model, fine-tuned on intent detection tasks. Further, we have proposed a joint training framework and designed 2 regularizers based on contrastive learning and correlation matrix respectively to increase the isotropy of the feature space during fine-tuning, which leads to notably improved performance on few-shot intent detection. Our findings and solution may have broader implications for solving other natural language understanding tasks with pre-trained language-based models.